Okay, today I would like to start a new chapter, which will be symmetry in chemistry. So symmetry is actually a mathematical concept, but has many applications in chemistry. Therefore, I would like to briefly review the principles of symmetry and how it relates to mathematical theory, and then apply the concept of symmetry to practical problems in chemistry. So symmetry can help us to solve many problems in chemistry. First of all, chemistry is strongly related to structures. So molecules and solid state materials all have structures, and symmetry can help us to classify and categorize the structures of molecules and crystals. Further, symmetry can help us to understand chemical bonding, and in particular in this course we will apply symmetry to molecular orbital theory. It can also help us to predict vibrational spectra and determine optical activity. So let us start from the very beginnings, and let us first ask how we can actually define symmetry. So symmetry is something which is pretty much omnipresent. We are surrounded by more or less symmetric objects every day. So we have a good intuitive idea what this is, but how could we scientifically define it properly? So generally, we can say that symmetry defines the self-similarity of an object. So if an object has many parts that are similar to each other, then that object has a high self-similarity, and we would think of it as quite symmetric. If an object does not have many parts which are similar to each other, then we would perceive it as less symmetric. So for instance, we have here a beautiful butterfly, and what we can immediately see is that the shape of the left wing of the butterfly is kind of similar to the right wing of the butterfly. For that reason, we perceive this butterfly to be symmetric. If the right wing had a shape which was very different from the left wing, we would perceive it as non-symmetric. So that is a very qualitative picture. Now, how can we actually quantify symmetry? And we can do this with the help of so-called symmetry operations and symmetry elements. So what is a symmetry operation and what is a symmetry element? So a symmetry operation is a movement around a point, a line or a plane into an equivalent indistinguishable orientation. So after we have carried out that movement, our object cannot be distinguished from the original object. So we carry out these symmetry operations around symmetry elements, and symmetry elements are either points, lines, or planes about which the symmetry operation is being carried out. So therefore, our task is to find what are the symmetry operations in an object and what are symmetry elements in an object. If we can find all these and sum these up, then we have determined the symmetry of an object. So let us therefore go through all the symmetry operations and elements that exist. So the most simple symmetry operation is the so-called identity operation. The identity operation is typically symbolized by a capital letter E. This is the so-called Schoenflies notation of the symmetry operation named after Schoenflies, who has developed them. So the identity operation says nothing else but that every object is self-similar to itself. So when we do nothing with this object, then, well, this object is, well, transformed into an indistinguishable form. Also, therefore, this identity operation exists. So naturally, this operation is present. In any object, of course, the identity operation is somewhat trivial from an understanding perspective, but it's actually necessary in order to make the mathematical framework around symmetry group theory complete. For that reason, we need to consider the identity operation. So now the next symmetry operation to consider is the property, the proper rotation operation, which is symbolized by capital C, followed by a subscript number and a superscript number. So n and m are simply integer number. So what is a proper rotation operation? Is a counterclockwise rotation about a proper rotational axis, which is symbolized also by a capital letter C, followed with the subscript n by an angle of 360 degrees over n. So n defines the so-called order of the principal axis. So for instance, if n is equal to 2, we have a C2 axis, and we would rotate around 360 degrees over 2, where that is 180 degrees. After we have done this rotation, our object would need to be indistinguishable from its original form. If, for instance, n was equal to 4, we would rotate around 360 degrees over 4, which is 90 degrees. And after a 90-degree rotation, our object would be indistinguishable from its original form. So what does the superscript m mean? This just indicates how many times the symmetry operation is being carried out, whether it's carried out 1 time or 2 times or 3 times, or another integer number of times. So for instance, a C4-2 operation would mean that we rotate 2 times around 90 degrees. Okay, so the proper rotation operations have a number of properties that are important to consider. So one important property is that when we actually rotate n times around a proper rotational axis, Cn, then that's the same as the identity. So for instance, when n is equal to 2, then we would rotate 2 times around 180 degrees. So that's the same as rotating by 360 degrees, and that's the same as not rotating at all, because all our points in the object are in their original position. For that reason, we can say this is the same as the identity. If we had a C4 axis to consider, for instance, then we would need to rotate 4 times around that C4 axis to reach the identity. That is because 4 times 90 degrees is also 360 degrees. If you rotate by n plus 1 time, that's the same as just rotating 1 time, because when we rotate n times and reach the identity and rotate 1 more time, well, that's the same as just rotating one time. Okay, so now we can have multiple different proper rotational axes in an object. They can have a different order. So the axis with the highest order is the so-called principal axis. So this is a term that you need to be familiar with. When you look for proper rotational axes in an object, you usually look first for the principal axis, the axis with the highest order, and then determine axes of lower order. So now it can be that you can have multiple different axes also of the same order. And if they transform that object in a non-equivalent way, we can also say in a non-conjugate way, and you will learn about the mathematical definition of conjugation shortly, then we need to distinguish them by primes. Okay, and the more bonds an axis contains, the less many primes it gets. And an axis which runs along a principal axis always gets the lowest number of primes. So let's do this by an example here. So here we have a square planar molecule that could be, for instance, hexachloroplatinate. And we see multiple proper rotational axes here. The first, let us look for the principal axis. So the axis with the highest order is in this case a C4 axis, and the C4 axis goes to this central atom here, and it runs perpendicular to the square plane of the molecule. So obviously, as we rotate by 90 degrees, all the peripheral atoms here would move. Okay, they would rotate by 90 degrees, and after the 90-degree rotation would be complete, our object would be indistinguishable from its original form. So now, in addition to this C4 axis, however, we also have C2 axes, and we have multiple ones. So we have one C2 axis here, which stands where actually just the C4 axis runs. This axis exists because we can also just rotate by 180 degrees to make the molecule superimpose with its original form. But we also have two C2 axes that go to these two bonds and these two bonds respectively. And then we have two more C2 axes which bisect the bond angle between the central atom and the two ligand atoms. So these are these two. Okay. So now, how do we label them properly? So first of all, we have to consider this one here, which runs parallel to the principal axis. Therefore, it gets the lowest number of primes. Then we have those that go through the bonds here. So they contain more bonds than the other two, which actually bisect the molecule here. Okay. Therefore, these two get both 1 primes. One can easily see that those that transform the molecule in a similar way, they're actually conjugate, and therefore they get the same number of primes. This gets 1 prime, and then the other two here, which bisect the molecule here, they are also conjugate relative to each other. They transform the molecule in a similar way, and they are getting 2 primes. They do not contain any bonds. Okay. Now, in addition to proper rotational axes, Now let us sum up. What proper axes do we have? Well, we have C4, we have the C2, we have two C2 prime, and we have two C2 prime prime. So now what symmetry operations are associated with these? So when we count the number of symmetry operations, then it's important that we do not consider symmetry operations twice. Okay. So now that means that we do not consider a number of symmetry operations associated with these symmetry elements. So for instance, when we look at the C4 axis, then in order to reach the identity, we would need to consider the C41, the C42, the C43, and the C44. Okay. Now the C44, however, we know is the same as the identity. So by convention, we choose the more simple symmetry operation. So we choose to list the identity and not the C44. So now the C42 is actually the same as the C21. Okay. So if we rotate 2 times counterclockwise around the C4, then that's the same as actually rotating only 1 time around this C2 here. Okay. The points in the object are getting transformed in exactly the same way. Okay. Therefore, these symmetry operations are identical, and we should only list one of the two. So by convention, one lists the simpler one, which would be the C21 and not the C42. Okay. Then the C43 is again a unique symmetry element. Therefore, we have to list it in addition to the C41. So further, we need to consider that for the C2 axis, we reach the identity when we rotate 2 times around the C2 axis. Therefore, we do not count the C22. We also don't count the C2 prime 2 and the C2 prime prime 2 because they're again the same as the identity. That means that our unique symmetry operations associated with the symmetry elements are the C41, the C43, the C21, then 2 of the C21 prime and 2 of the C21 prime prime. Okay, so we have 2 to consider here because we have 2 axes for each kind. All right, so now we have really said everything about the proper rotational axis. Now let us consider another symmetry operation, which is the reflection operation. In the Schoenflies symbolism, the reflection operation is abbreviated by a small sigma symbol. So the reflection operation is carried out around a reflection plane, also often called a mirror plane. And there are 2 different kinds of mirror planes and reflection operations. We can either reflect at a so-called vertical mirror plane, or at a so-called horizontal mirror plane. So what is the difference? When we have a horizontal mirror plane, then that mirror plane stands perpendicular to the principal axis. And when we have a vertical mirror plane, then we have our mirror planes passing through principal axis. So horizontal mirror plane is designated sigma h, and the vertical mirror plane is designated sigma v, and the associated operations are being denoted the same. So now here's an example that illustrates the difference. We have here trigonal planar molecule, the BH3 molecule. And in that molecule, we have a C3 principal axis that you see here. As we rotate around that C3 axis, we basically rotate around the three hydrogens by 120 degrees. The bond in the middle does not change its position. So now you see that you have here a horizontal mirror plane. Why is it a horizontal mirror plane? It is a horizontal mirror plane because it stands perpendicular to this principal axis here. Okay. Now the symmetry element is present because when we carry out a symmetry operation around it, then our molecule is indistinguishable from the original form. So now you see that in this case, the atoms do not move as we carry out the symmetry operation, but nonetheless, that symmetry operation is present because each point above the mirror plane is afterwards below the mirror plane in each point of the object, which is below the mirror plane is above the mirror plane when we, after we have carried out the symmetry operations. So for instance, the top half of this hydrogen atom, okay, will be mirrored below the mirror plane, and the bottom half of this hydrogen atom will be mirrored above the mirror plane. And the same happens to all the other atoms, and we can see that points in space have moved, points in the object have moved, even though the atoms themselves haven't moved. But they don't need to do this in order to show that the symmetry element is actually present. Okay, so now in contrast to this mirror plane here, which we designate sigma h, we have here, in addition, three vertical mirror planes, sigma rho. So these three vertical mirror planes contain the three boron hydrogen bonds. Okay, you see that this mirror plane here contains this boron hydrogen bond. This mirror plane here contains this boron hydrogen bond. And this mirror plane here contains this boron hydrogen bond. Okay. Now you see that all three mirror planes contain the C3 axis. Okay, so this the 3 axis is part of these three mirror planes, and therefore we call this mirror plane, or these mirror planes, vertical mirror planes. They are all equivalent. They transform the object similarly, so therefore they're grouped together and they're not getting distinguished by primes. We can briefly check how this mirror plane transforms the object. So for instance, if we put ourselves on this mirror plane here, which goes to this BH bond, then the boron atom wouldn't move, and this hydrogen atom wouldn't move. Okay, but the other two hydrogen atoms here, they would swap up their positions. Okay, if we picked this mirror plane here, okay, which contains this boron hydrogen bond, then this hydrogen atom wouldn't move, but these two hydrogen atoms would swap up their position. Okay, so now how many operations do we have per symmetry element? So in the case of the mirror planes, the situation is very simple. If we mirror an even number of times, then that produces the identity. And when we mirror an odd number of times, then that is the same as reflecting just one time. Therefore, there's only one unique symmetry operation associated with each mirror plane. Okay, so we only need to consider sigma 1 and no other symmetry operation. Okay, so there's a special kind of vertical mirror plane that we need to consider, and this is the dihedral mirror plane. But before we go to that, here's an example actually where we have several sigma v mirror planes that we need to distinguish by primes. So for instance, in the water molecule, we have one vertical mirror plane, this one here, which lies within the water, in the plane of the water molecule, while there's an additional one, this one here, which stands perpendicular to the water molecule. Okay, so obviously these two mirror planes are vertical mirror planes because they both contain this C2 axis here, but they are transforming the object differently. You can see this, for instance, by the fact that when you carry out the symmetry operation around the vertical mirror plane, which lies within the plane of the molecule, the atoms actually do not move, okay? While as we carry out our symmetry operation around this vertical mirror plane, which bisects the object, then the hydrogen atoms would swap up their positions, okay? For that reason, we need to distinguish the two vertical mirror planes by primes. And again, the one which contains the larger number of bonds has the smaller number of primes. So this means that this one here gets 0 primes, it's our sigma v, and the other one gets 1 prime, and we call it the sigma v prime. Okay, but now let's go to the dihedral reflection planes. They are a kind of special kind of vertical mirror plane, and they're denoted sigma subscript d. So when we have a dihedral reflection plane, then we have a plane that bisects the angle between two C2 axes. Okay? So you see actually, sorry, an example for that here. So here we have again our square planar molecule, and recall we had these C2 axes going through these two bonds here, the first one, and the other C2 axis going through the other two bonds. Okay, so now we have vertical mirror planes that contain the C4 axis, which actually stands here, that bisect the angle, okay, between the bonds. And at the same time, it also bisects the angle between two C2 axes. And because of that, these vertical mirror planes are called dihedral mirror planes. Okay, now let us continue with these considerations. There are two more symmetry operations to consider, and the first one is the so-called inversion operation, the inversion operation is denoted with a symbol I. Okay, so what does an inversion operation do? The inversion operation moves all the points of an object through an inversion center, also called a center of symmetry, to the other side. So in this case, we have a point as the symmetry element, which is an inversion center or center of symmetry. So generally that means that for every point in the object which has the coordinates x, y, z, an inversion operation converts the coordinates to minus x, minus y, and minus z. So let us see by example what that actually means. So for instance, octahedral molecule like SF6 is shown here, has an inversion center in the center of the octahedron. And any point in this object can be moved through that center of the octahedron to the other side. After that, the symmetry, the object will look indistinguishable from its original form. Okay, so now, for instance, this atom labeled 1 here would move through the inversion center to the other side into the position of atom 2. Okay, then it would be here. So fluorine atom number 2 would move through the inversion center to the other side, and then would be in this position. So fluorine atom number 3 would move through the inversion center to the other side, and it would be here. So atom number 4 would move through the inversion center to the other side, and then it would be here. Atom number 5 would move through the inversion center to the other side. So it would now be in this position, and atom number 6 would also move through the inversion center to the other side, then being in this position over there. So how many inversion operations do we have per inversion center? So again, everything is pretty simple here. If you carry out symmetry operation even number of times, for instance 2 times, 4 times, or 6 times, then that's the same as the identity. When we carry out the operation an odd number of times, then that's the same as carrying out the operation only 1 time. So therefore the sigma 1 is therefore the only unique symmetry operation associated with the inversion center. All right, so now the last operation to consider is the so-called rotation reflection operation, which is associated with the Schoenfeld symbol capital S subscript n. So this is the most complicated operation because it requires a combination of movements. First a rotation and then a reflection. Only after we have carried out both of them, our symmetry operation is complete. So the rotation reflection operation, sometimes also called an improper rotation, that is because after the rotation, the operation is not complete yet. Our object is not necessarily in an indistinguishable form yet. We need an additional reflection in order to make the symmetry operation complete. So where do we reflect? We always reflect perpendicular around the improper rotational axis around which we rotate. So here's an example. Here we have the methane molecule, which is tetrahedral and has and S4 improper rotational axis. So that means that to bring the object into an indistinguishable form, we would need to first rotate by 90 degrees and then reflect perpendicular to the axis around which we have rotated. So now, where is such an improper rotational axis in this molecule? You see it actually here. This is the green line. And you see that this green line bisects the angle between the hydrogen atoms 1 and 2 and the carbon, as well as the angle between the hydrogen atoms 3 and 4 and the carbon. Okay, it goes actually through two opposite edges of the tetrahedron that would inscribe the molecule. So that means that if we want to reflect, we have to reflect perpendicular to this axis, and you see the respective plane, reflection plane here. All right, so now let us see how do the atoms move as we carry out that symmetry operation. Okay, so first we have to rotate 90 degrees. Okay, so if you rotate 90 degrees, then this hydrogen atom 1 actually moves to the back. Yeah, it points now to the back. This hydrogen atom 2 rotates to the front and now points to the front. This hydrogen atom number 3 now points upward, and our hydrogen atom number 4 points downward. So now you can see that this molecule here does not superimpose this molecule here. So if you just shift this to the left, it will not superimpose the original molecule. So that means, so that proves that our rotation is not proper. Yeah, it's improper. We need to reflect now at this reflection plane perpendicular to our improper rotational axis to make our molecule superimpose. Now let's just do that. Okay. Now reflect at this plane. Then we move here, this atom number 3, through this plane to the other side. So now we have it here. Our atom number 4 moves also through this plane to the other side. So now it's here. Now our atom number 2, okay, which points to the front, will also move to the plane to the other side. Okay, still pointing to the front. And our hydrogen atom number 1 will move to this plane over there, now still pointing to the back. Okay. So now you see that the produced molecule superimposes the original molecule. Okay. So the hydrogen atoms are not exactly in the same position, but we do not consider their labeling. Okay, we only check if we can superimpose the two molecules, and indeed we can impose these two molecules. So what this also shows that the presence of a proper rotational axis in the mirror plane is not necessary for Sn to exist. Okay, so this axis around which we rotated is an improper axis. Okay, just rotating does not make the molecule superimpose, and the same is true for the reflection. So if we just reflect but not rotate in addition, then that also doesn't make the molecule superimpose. Okay, so now the rotation reflection operation has a number of interesting properties we want to consider in the following. Okay, so first of all, an S1 operation is always identical to a sigma operation. Okay, so that means that we would actually not need a sigma operation. It's a separate symmetry operation, but by convention we use it because an rotation reflection operation is a two-step process, whereas a reflection alone is a one-step process, which is easier to do in the human mind. Therefore, by convention, we use reflections over S1 symmetry operation. So why is an S1 identical to a sigma? That is because the subscript 1 means that we rotate by 360 degrees, and that's the same as not rotating at all. And so we actually only reflect, and if you only reflect, well, then that's the same as a regular reflection operation. Okay, so another property is that an S2 rotation reflection is always identical to an inversion. So also the inversion is actually not a unique symmetry operation. It can be expressed by a rotation reflection operation. But again, by convention, we use inversions over S2 rotation reflections because, again, it's easier to do this symmetry operation in the human mind because an inversion is a one-step process, whereas an S2 operation is a two-step process. Okay, let's just show by example that an S2 is the same as an inversion center. S2 is the same as an inversion. So let's consider here again our octahedral SF6 molecule. We have previously shown how the fluorine atoms labeled from 1 to 6 move when we carry out an inversion. Okay, so if an S2 is identical to an inversion, then the S2 would need to move the points in the object in exactly the same manner. Let us just show if this is true. So when we carry out an S2, then that means we first have to rotate by 180 degrees. Okay? So let's rotate by 180 degrees around an axis which contains these two SF bonds here. Okay? So if we rotate around 180 degrees, then the atoms 1 and 2 don't move, but the other 4 atoms move. Okay, so atom number 3 rotates by 180 degrees into this position. So now it's here. So atom number 4 rotates by 180 degrees into this position here. So now it's over there. Atom number 5 moves 180 degrees into this position over here. And atom number 6 moves 180 degrees into this position. So now it is here. Okay. So now, next, we have to do a reflection. Okay. And we have to reflect perpendicular to the axis around which we rotate. So that means that our reflection plane is now the plane containing the atoms 3, 4, 5, and 6. So now as we reflect at this plane, the atoms 1 and 2 actually swap up their positions. Okay, so now 1 is over there, and 2 is over there. Okay, but the atoms 3, 4, 5, and 6, they don't change their position. Okay, and if we compare now, well, the resulting molecule with the molecule that's created just by the inversion, we see that they are identical. Okay? So that means each point in the object is at the same identical position, proving that S2 is indeed identical to I. Okay, so now what other properties does the rotation reflection have? So one other interesting property is that when the order of the improper rotation reflection is even, then that means that the molecule also contains a proper rotation that has half of the order as the improper rotation. Okay. Another property is that we need to rotate, reflect an n number of times in order to reach the identity. Okay. So the number n is equal to the order of the improper rotational axis. All right. However, when the order of the improper axis is odd, then that means that we also have to have a proper rotational axis with the same order. And in addition to that, we also have to have a horizontal mirror plane. So in this case, when we rotate an n number of times, then we do just the same as carrying out this horizontal reflection. We actually have to rotate 2n times in order to produce the identity. So now let's look by example if this is actually correct. So here we have the PF5 molecule, which is trigonal bipyramidal. Sorry. And this molecule has an S3 improper axis. Okay, so this S3 axis stands here, and we rotate around this axis. That means that we must reflect perpendicular to it. Okay, now let us just carry out that operation and see how the atoms move, and show that we now have to carry out the symmetry operation 2n times in order to produce the identity. Okay, so we again label our fluorine atoms 1, 2, 3, 4, 5, and see how they move as we carry out the symmetry operations. So we would expect that we would have to carry out the symmetry operation 6 times to produce the identity, and only 3 times in order to just reflect. Okay, so an S31 means that we have to rotate counterclockwise here. So that doesn't change the positions of F1 and F2, but it moves F3 into this position, and F5 into this position, and F4 into this position. Okay, you see this here. F3 is now here, F5 is now over there, and F4 is here. After that, however, we have to reflect. Okay, we have to reflect here in this equatorial plane. So reflection doesn't change the position of F3, F4, and F5, but it swaps up F1 and F2. So F1 is now here, and F2 is now over there. Okay. Now, if we do this for another time, then as we rotate, we again move around the atoms in the equatorial plane. So F3 actually moves here, F5 moves over there, and F4 moves over there. So you see you have F4 now here, F3 now here, and F5 is over there. So as we reflect, we swap up F2 and F1. So F2 is now here, and F1 is now over there. All right. So the next step, we carry out an S33, which is now the same as a sigma H. So F4 moves over here, F3 moves over there, and F5 moves in this position after the rotation part. Okay, you see F4 is now here, F3 is now over there, and F5 is now here. So now the reflection part again swaps up F1 and F2, but doesn't affect the equatorial atoms. So F2 is now here, and F1 is now over there. So if we compare this molecule here with this molecule over there, we see that there's just a reflection operation in between them. Okay, so F5, F3, and F4 are in the same position. You can compare that. And just F1 and F2 have swapped up. As we go directly from here to here, we have just carried out a sigma H. So now we still need to do 3 other operations. So if we do the 4th one, again, we rotate these 3 by 120 degrees. So F5 moves over here, F4 moves over there, and F3 moves into this position. See, we have now F3 here, F5 over there, and F4 we have here. So again, the reflection swaps up F1 and F2. So we have F1 now here and F2 over there. All right. Now let's do this one more time. And then we move F3 into this position, F5 into this position, and F4 into that position. So we have now F4 here, F3 over there, and F5 over here. Again, F2 and F1 swap up their positions. Now F2 is here and F1 is over there. So now if we do this for the 6th time, okay, then we reach again the original molecule with all fluorine atoms in the same positions. Let's just show this. F4 moves into this position. Okay, we have it here. F3 moves into this position, so we have it here. And F5 moves into that position. So we have it over there. Again, and F1 and F2 swap up. So F1 is over here, and F2 is over there. All right. 2 more things to consider is that actually the S32 is the same as the C32. Okay, that is because reflecting 2 times is the same as not reflecting at all. Therefore, actually, we just rotate 2 times by 120 degrees, which is the same as the C32. And in addition to that, an S34 is the same as a C31. That is again because rotating an even number, reflecting an even number of times is as though we would not reflect at all. Okay. Therefore, we're actually just rotating 4 times around 120 degrees, which is the same as rotating around just around 120 degrees, which is the same as C31. All right. So I see our time is over. We are already 4 minutes over the time. So I'll stop at this point. And I will illustrate in the next class also an example with an even number, with an even order, and then start with point groups. So let us stop at this point.